As an example of parameters and families of functions, we'll take a look at an example that involves Newton's law of heating and cooling. So Newton's law of heating and cooling. So basically the situation here is you have a room and you might have a cup of coffee, right? So you have a hot cup of coffee in a cold room. So you have an ambient temperature, so you call it R, and then the cup of coffee has the temperature U of T. So this is the temperature of your object as a function of time. So Newton's law of heating and cooling says that the rate of change of the temperature of an object is always proportional to the difference between the temperature of that object and the surrounding room that it's located in. And as a result of that basic assumption, you can derive an equation using differential equations for U of t. And that equation is as follows. So U of t is equal to R plus U0 minus R e to the minus kt. So following from Newton's law of heating and cooling, one can derive this equation down here. So this equation contains three parameters. So three parameters. So R, which is the ambient temperature, U0, which is the initial temperature, and then K, which is basically a constant. So the larger the value of K, the quicker the temperature of your object approaches the temperature of the room. And so basically during the derivation of this equation, you would treat R, U0, and K as constants. And you do some mathematics and you get this equation that now depends on R, U0, and K. And they're still constants because for a given object in a given room, you'll have a given physical situation that will lead to given values for R, U0, and K. This could be more than just a cup of coffee cooling down in a room. It could be a frozen turkey heating up in an oven, for example. So any object that's initially has a different temperature than the surrounding room, this equation can describe that. So let's look at it in terms of function transformations. So if we start with just f of t is equal to e to the t, how do we transform this to get it to look like u of t? And then how do we use those transformations to understand what the graph of u of t looks like? Well, you wouldn't necessarily have to go through all these transformations to get a feel for the graph of u of t. When I look at this, I see, okay, e to the minus kt, that's going to go to 0 as t goes to infinity. So this term is decaying to 0. And so if this term is going to 0 as t goes to infinity, u of t is going to approach the room temperature, which makes sense. If you have a hot cup of coffee and you come back 5 days later, it will probably be the temperature of the room. If you have a frozen turkey and you put it in a 400-degree oven and you leave it there for a couple of days, you leave your oven on, come back, the turkey is probably going to be at 400 degrees, or pretty close. So something that decays toward R. And then the initial value, or the vertical intercept, is u0, because when I plug in 0 for t, e to the 0 is 1, so I get R plus u0 minus R, which is just u0. So we get something that starts at u0 and it decays towards R, just like that. But in terms of the functional transformations, we start off with e to the t, so let's start at 1, and it decays. One step ahead of myself. It grows. So it's like that. There's e to the t. And then you can say, well, g of t is equal to f of kt. Right, so it's equal to e to the kt. So now we just have something that grows faster. So we've affected the growth rate. So there's e to the kt, e to the t. So next we can say h of t is equal to g of minus t. So in other words, it's e to the minus kt. So that is our horizontal reflection. So now we get something that starts at 1 and it decays with the appropriate rate. So next we multiplied it, so let's say k of, let's say m hi, so m of t is equal to u0 minus r times h of t. Right, so now we have this vertical stretch. So the new function, instead of starting at 1, is going to be starting at u0 minus r and then still decaying. So we did a vertical stretch. And then finally we added r to get to u of t is r plus m of t. So this is a vertical translation. So everything gets picked up by the same amount. And we're at something that looks like this. So it starts at u0, and instead of decaying to 0, it decays to r. So you can see that there implicitly, usually I don't go through and think about all these different transformations, but if you have a function like this, so this is actually a family of functions that depends on 3 parameters, it really is just a bunch of transformations of a basic exponential function. So you can always understand some of these families of functions in that way. In fact, quite often you'll have a family of functions that's obtained by just a number of basic elementary transformations, these horizontal stretches, compressions, and so forth. So now let's actually do an example with this. So u of t was r plus u0 minus r e to the minus kt. Okay, so we have a hot cup of coffee. So initially 180 degrees, and then it's in a room that's 70 degrees. So the ambient temperature of the room is 70 degrees, and your hot cup of coffee is initially 180 degrees. And then 3 minutes later, your coffee is 150 degrees. So how long will it take for your coffee to reach 100 degrees? So you have a hot cup of coffee, initially 180 degrees, in a room that's 70 degrees. 3 minutes later, your coffee cools down to 150 degrees. How long will it take for the coffee to be 100 degrees? Okay, well, we know that R is 70 and U0 is 180. So U0 minus R will be 110. So basically our function is just going to be 70 plus 110 e to the minus kt. And then we also know that u of 3 is equal to 150 degrees. So first we need to solve for the parameter k. And we'll use the fact that after 3 minutes, the coffee is 150 degrees. So we have 150 is equal to 70 plus 110 e to the minus kt. 150 minus 70 is 80. So 80 is equal to 110 e to the minus kt. So we have 8 over 11 is equal to e to the minus kt. Take the ln of both sides. Ln of 8 over 11 is equal to minus k times t. So therefore, and then, okay, so really up here I wanted to say e to the minus 3k, right? Because I want to equate 150 with u of 3. So this should be u of 3. So I'm going to plug in 3 for t. It's not too late, so I'm going to plug in the 3 for t. Right. So this is after 3 minutes that the coffee is 150 degrees, so we should equate 150 with u of 3. So we get this, so therefore k is equal to minus 1/3 ln of 8 over 11, which is equal to 1/3 ln of 11 over 8. And what happened here was I took this minus 1 and moved it up to the exponent, and the minus 1 took the reciprocal of 8 over 11. So you have k is equal to 1/3 ln of 11 over 8. All right, so now let's use this to go back and solve for the time. So we have u of t which is 70 plus 110 e to the minus kt, where k is 1/3 ln of 11 over 8. All right, so now we know that, now we want to solve for u of capital T is equal to 100. So find the time at which the cup of coffee reaches 100 degrees. All right, well, so we set 100 equals to u of capital of T. And we know what k is this time, so we do the same game. So 100 minus 70 is 30. Divide by 110. Take the ln. So the final time will be equal minus 1 over k ln of 3 over 11, which is equal to 1 over k ln of 11 over 3. Now, that's equal to, so 1 over k is going to be 1/3, so we get 3 ln of 11 over 3 divided by 11 over 8, no, 11 over 3 divided by 11 over 8. And let's see what that we get. So 11 over 3 ln divided by the ln of 11 over 8, and then times 3. So about 12 minutes. So it's 12.239922. So 12 minutes, 14 seconds. So it will take approximately 12 minutes and 14 seconds for the coffee to reach 100 degrees. So enjoy it while it lasts.